Okay, so what I want to do today is start talking about approximate message passing algorithms. So approximate message passing. Which I'll abbreviate as AMP. Okay, and so most of what I'll talk about over the next few days comes from a tutorial I wrote with some co-authors. So it's a unifying tutorial on AMP. And this is with a bunch of dudes from Cambridge. So Feng, Venkataramanan, myself, and Samworth. Okay, so all right, so what is AMP? Okay, this is a class of efficient iterative algorithms. Generally, for solving, kind of statistical estimation problems. So, what we should have in mind is things like, high dimensional linear regression, like we talked about on Monday. Things like low rank matrix estimation, that Josh is talking about, stochastic block model, these sorts of problems. It can handle more general types of sort of linear regression. So, things like phase retrieval, which is kind of like an application that's used a lot in like microscopy, and other kind of general, like problems related to generalized linear models, right? So things like logistic regression and other kinds of regression, right? So, okay, so there are kind of like, I think, sort of two attractive features of AMP that have, kind of made it useful and are the reason for its kind of popularity these days. So, okay, so two attractive features. Okay, so the first is that you can sort of easily incorporate some sort of prior knowledge on the signal or the thing I'm trying to estimate. So, you can easily use prior info on signal structure, right? So when I say the signal, I just mean kind of like the target of estimation. So like in like the linear models, right? I'm thinking of like that vector theta as being the signal. This is the thing I want to estimate. Like this nomenclature, comes more from like kind of engineering applications, like high dimensional linear regression is compressed sensing as well, right? There's actual like people who do this like in the wild, right? And it is like a signal. Right, and so this is nice because, kind of like what we've done the last few days is convince ourselves that if we want to do anything like in high dimensions, then we need to assume some sort of structure, right, in order to be able to solve the problem. So in particular, like easy to incorporate like sparsity into the problems and other sorts of structures. And so the other thing that's nice is that every iteration of the algorithm, so the algorithm iterates and returns kind of vector estimates of whatever, you know, you're trying to estimate here. And what the kind of theory gives you is precise asymptotics. So I just mean exact sort of asymptotic characterization of the iterates of the algorithm, you know, in this sort of high dimensional limit. So in the limit where, you know, n and d both go to infinity with, you know, some like fixed aspect ratio. So technically it also encompasses like low dimensional asymptotics as well, but this is like a, you know, we would call this like a proportional high dimensional regime, right? You can imagine other high dimensional regimes, right, that aren't proportional, where like the dimension actually grows like more, you know, exponential in n or something. But AMP studies this like proportional asymptotic regime. Okay, and so then the uses of AMP are mainly kind of the following two. So the first is like you can kind of use the precise asymptotics of the algorithm to give you like precise asymptotics for like your solutions to these sorts of problems. So you know, doing that allows you to analyze, you know, statistical properties or characteristics of estimators. Right, so you know you can use AMP to kind of, you know, if you're doing like rank 1 matrix estimation to recover like the spike that gives you the rank 1 aspect, right, and then you can study properties of that spike, like, you know, the sparsity or the mean squared error to the truth and these sorts of things. You can also use AMP to study statistical computational gaps, which I don't think I'll talk about too much, but maybe I'll mention a little bit in a few days. But what I kind of mean here, right, is in a lot of problems, you know, we have kind of information theoretic limits, right? So these are things that Jesus talked about a bit, right? We'll have information theoretic limits that say, okay, if the sample size is, you know, so big, we should be able to recover the signal accurately. But then when we look at, you know, the algorithms that we know, like the efficient polynomial time algorithms, right? They can't actually perform at these limits. So this is kind of what I mean by this sort of gap, right? Sometimes it's like we can do better if we don't care about being efficient, but when we care about being efficient, you know, we're not performing optimally. And so the role of AMP here is that for, you know, a number of problems, you know, it's kind of conjectured that AMP is optimal amongst polynomial time algorithms, at least if you're trying to like minimize the mean squared error between your signal and the truth. So what that kind of means, right, is we have a bunch of classes of algorithms, like SQL methods, sum of squares, low degree polynomials, these sorts of things that are like classes of algorithms that the computer scientists have found that, you know, seem to be optimal on these kind of like random optimization problems and these sorts of things, right? And AMP is kind of performs at the same limits as those other algorithms, and there's even a line of work that kind of shows that all of these algorithms are equivalent. So you can show that, you know, AMP is equivalent to like low degree polynomials and vice versa and these sorts of things. You know, you can also like kind of show that if you want to do any first order method for, you know, optimizing random cost functions, in fact, that's an AMP algorithm. So you can also use AMP to get kind of like lower bounds on estimation error, on the estimation error of like any first order method and these sorts of things. So these are kind of the ways that people use the algorithm. So I guess like what's like kind of like conspicuously missing from this list, right, is that AMP is not so much used actually as a way to solve the estimation problems. Like it's not often used as a solver. The reason being it needs kind of specific assumptions. Like there has to be some Gaussianity running around. So if you think about like high dimensional linear regression, if you're a statistician, then things are data and the assumptions of AMP are too strong. So usually it's like if you want to do the lasso or something for high dimensional linear regression, you should still do this with like proximal gradient descent. You could do it with AMP, and if the assumptions are met, then AMP will converge more quickly than the gradient descent. But the assumptions are like the matrix has to be Gaussian and these sorts of things. So the only place kind of where AMP is used actually as a solver is in sort of engineering applications where you're kind of designing the system, so you can you're like God, right? So you can make the matrix IID Gaussian or something if you need to. Okay, so just a few words on like the background. So in the beginning, sort of AMP was derived from loopy belief propagation algorithms, and kind of the like first instance of this I know. So kind of the first example of relaxing belief propagation that we could find was in CDMA, which stands for coded denoising multi-user access, I think. Hold on, let me make sure. Let me look at my notes and make sure that's code division multiple access. Yeah. So this is like this is a kind of like channel access model that's used in like radio communications, right? And so this was like work by Giuseppe Caire, 1R, Mueller, and Tanaka from 2004. Right? And kind of after that, there was a number of different works that sort of derived AMP from systematic approximations to BP. And so this was sort of done like in a like problem-specific way. So the early work did this for like linear regression or like compressed sensing, right? They're kind of the same thing depending on which community you come from. And this, I'm thinking this is like Montanari gave a nice, sort of, he wrote a book chapter in like 2010 that goes through how you like derive AMP for lasso from like a min-sum message passing algorithm on a completely dense factor graph that represents like the linear model, right? There's also, some of the early work in AMP was Donahoe, Malecki, Montanari, around the same time. This is like 2009. Some French dudes were also getting at these same ideas, kind of led by Florent Krizacala, who was at that point at the ONS, and now is at EPFL. And then, for subsequently, right, they derived AMP for like generalized linear models. This was Sandeep Rangan. And then the low rank matrix estimation. So this was again by the French guys, so Lesueur, Lesueur, L-I-S-E-U-R, Krizakala, and Zedebarova. That was a little bit later, like 17 or so. So I list these references because I'm going to take a little bit of a different approach for deriving AMPs. So I won't use the derivation from message passing just because kind of like you set up like a little bit of a different message passing algorithm for each like model, and then you go through the same steps. And at some level, you know, it's like if you're really comfortable with BP, I think this can be like a useful way to find AMP. But if you like don't know much about belief propagation, it's like pretty abstract, right? And at some level, like you know, you start with a loopy belief propagation algorithm, which there's no theoretical guarantees for anyways. So it's kind of a weird launching off point, right? To start with something that often seems to work, but you know, we can't prove much about it, right? And then you get the AMP algorithm. So kind of in short, like the approximation is the following, right? When you do belief propagation, what you're doing is, you know, kind of passing messages along the nodes of a graph, and these messages contain like distributional approximations for, you know, like the thing you want to estimate, like the elements of the thing you want to estimate and these sorts of things. And so the approximation is sort of twofold. In one sense, you approximate the full beliefs with just kind of with Gaussians, right? So instead of passing like these full distributions, you just pass like 2 moments, right? And assume everything's Gaussian. And the other approximation kind of comes from the fact that, you know, if you're doing like a completely, you know, dense sort of message passing, so I'm imagining like a factor graph that's like this, right? And it's completely dense. So like all these edges are here, right? And so, you know, kind of like the one kind of key property of message passing, right, is like, okay, if I'm this node and I'm trying to decide what to send along this edge, then, you know, what I use to create that message is you know, the incoming message here and the incoming message here. I'm not going to use the incoming message along the edge I send. And so sort of the idea is when, you know, you have this completely dense factor graph, it's like basically the messages that all of these guys are sending at any iteration are more or less the same, right? Because they're getting, you know, all of the same messages and just leaving out one, right? So they're all kind of combining things and sending something that's almost looks exactly the same, except for the you know, the choice of what to leave out. And so that, you know, the approximation then is like, okay, well, all of the messages coming from this side over here look essentially the same, so let's just call them the same. All of the messages coming from this side over here are essentially the same. So you go from like, you know, m times n messages or whatever to just like one iteration or one message at each like kind of iteration. So those are the two sort of approximations that happen when you go from BP to AMP. But, you know, it's like actually doing it is a bunch of Taylor expansions and these sorts of things. Okay, so the approach I'll use to introduce AMP is the following. So it's a bit more like mathematical, I guess. So the idea is I'll introduce sort of an abstract AMP algorithm. So the idea is that, you know, this is it's an AMP algorithm, but it's not tied to any specific problem. So it's not like trying to recover any specific estimate. It's just, kind of an iteration involving like a random matrix and like Lipschitz denoisers acting on the previous iteration. And we'll look at that because it's sort of like the way you can get all the AMP algorithms for all these other problems is to kind of build up from this abstract AMP, and the abstract AMP is nice because you can kind of understand like why you get precise asymptotics and these sorts of things. Kind of the main result for the abstract AMP is the following. So the empirical distribution of the elements of each like vector iterate, so of each iterate, are Gaussian is essentially the kind of main result. Like they're approximately Gaussian with mean and variance determined by kind of the so-called state evolution, which is just a sort of scalar recursion that determines the performance of the algorithm, right? So it determines the performance of the algorithm in the sense that it tells you like the mean and the variance of the elements of the iterates at each step. Okay, and so then kind of the next goal is I'll connect like the abstract recursion to AMP for low rank matrix estimation. And I mean, this will probably happen like on Monday next week, right? So kind of this is like the example that I'll use to show how you can, if you want to like find an AMP algorithm for your favorite problem, right? Kind of what you can do is like start with the abstract AMP and then sort of build up in some sense. Okay. All right, so the abstract AMP I'm going to look at is, like I said, it's not related to any problem. The idea is it's just going to be like an iteration between a random matrix and like a Lipschitz function acting on previous estimates. And so in particular, the random matrix will be a GOE matrix, which we're probably familiar with, right? But I'll remind, right? So this is essentially just like a symmetric Gaussian matrix, right? So we'll say W is GOE of size n. If W is like is an n by n symmetric matrix, and we have the following. So the Wij are independent, for 1 less than or equal to I less than or equal to j less than or equal to n, right? So this says, if you look at like the diagonal and the upper triangle, right? These are all independent elements, right? And okay, so off the diagonal, these guys are, IID normal 0, 1 over n. right, for I not equal to j, I less than j, let's say. Right, and on the diagonal, we just double the variance, so they're normal 2 over n. Right, and so, okay, so the property that we'll use, right, is a kind of rotational invariance, right? So, you know, if a matrix W is GOE, and Q is any orthogonal matrix, right, then, you know, Q transpose W, Q is also GOE. Right. Okay. Okay, so then, all right, so here's an iteration with a GOE matrix, right? So this is what I'm calling the abstract AMP, right? So, okay, so I'm going to initialize with some vector h in, you know, Rn, and, you know, for t greater than or equal to 0, I'm going to define the following. I'll say mt equals ft ht, and ht plus 1 equals w mt minus bt mt minus 1, right, where, okay, so this is my abstract AMP, right, where, okay, so ft is just, this is a Lipschitz function. I'm thinking of it as like from R to R, so it acts like coordinate-wise. Right, and it could change with the iteration. Right, okay, so BT is what, okay, it's the gradient, or the, you know, sum of the first derivatives of ft prime ht I, right, and then, you know, my first step is, you know, h1 equals w times, you know, f0 h0, right? So, like, yeah. Yeah. Yeah, roughly, yeah. So, yeah, here it's a little bit, since it's like the symmetric version, it's, I'm not quite sure what the, yeah, but in the asymmetric version, yeah, so this is kind of the way to like one iterate is going one way and the other is, yeah, so okay, so I mean, the main thing we should think about here is like, okay, this is just like, this is just some algorithm that I've come up with, right, that you initialize it some way, right? You send that through some Lipschitz channel, right? Some Lipschitz function, right? And then whatever you get there, you just hit it with this random matrix, and you keep iterating that sort of process. And kind of the idea is that this term is sort of like some sort of momentum term or correction term that enforces the Gaussianity at each iteration. And so we'll try to see, you know, as best as I can do in, you know, an hour, if we can convince ourselves roughly that this is what's happening. Okay, so kind of another idea, right, is, you know, all of our results will be asymptotic in n. So here there's only one dimension because it's a symmetric problem, but all of the results will be asymptotic in n. So you kind of need to think of, like, you know, the initialization and like this random matrix as being like a sequence in n, right, that's growing in some sense. So that'll be how we study the asymptotics. Right?
Is there a stopping?
Yeah, so there's no sort of stopping time. So kind of the like guarantees we'll give is for any iteration t, if I allow n to go to infinity, then it's Gaussian. And so kind of, you know, then what you'll see is like, okay, so this is going to be Gaussian mean 0 with some variance, right? And so you can kind of like stop when the variance gets low or something. I mean, again, it's like it's abstract now, so we aren't like ever going to find a signal like or something. But eventually, kind of what you can do is like, you know, the guarantees will be like, you know, the mean square error between MT and the thing I'm trying to estimate is characterized exactly by, you know, my state evolution at time t, and so you can kind of iterate until that's like small enough or something. Okay. All right, so then, all right, so the kind of the key result, which I'm going to state informally now, and then we'll try to, you know, go through like at least the first step of the induction and see why it's true, and then we can kind of, you know, hand wave ourselves through the next step is the following. So this is kind of like the main theory for IMPA relates the state evolution, which again is like a deterministic scalar recursion, to the performance of the algorithm. So informally, the theory says the following. So if our initialization is independent of the randomness, then for t greater than or equal to 1, as n goes to infinity, the empirical distribution, which I'm going to call p hat ht, right? So sorry, this is the empirical distribution of ht, right? Converges almost surely to a Gaussian mean 0 variance tau t squared, where okay, so this is the state evolution. Okay, so tau t plus 1 squared is the expected value of ft tau t z squared, where z is just a standard Gaussian. Okay, and I'm going to initialize the state evolution. So this, I guess I'll say, like, okay, so this, tau t to tau t plus 1 recursion is, state evolution. And we're going to initialize with tau 1 squared equals the limit as n goes to infinity of 1 over n f0 h0 norm squared, which I'm gonna assume that's less than infinity, or things kind of don't make sense, right? Okay. Distribution that puts a point mass at each of the elements. So we have a vector, x1, x2, xn, right? And it's going to put, it's going to, the empirical distribution takes each value with probability 1 over n, right?
Yes, I guess the important things, if I want to say something, say about the norm, the norm
Yeah.
vector, square norm, whatever, that's a function of the empirical distribution.
Yeah.
For the distance of h of t to some other vector.
Yeah. Yeah, so eventually, you can kind of act like the elements have this distribution eventually, is kind of the idea of it. Okay, so, all right, so what I want to do for the rest of today is just try to see if we can see why is this true. Okay, so I'm going to give kind of like a heuristic proof. Okay, so so we give a heuristic proof. So how do you actually prove this? So you prove this basically by induction on the iterations. So you show, okay, at t equals 1, we're good, things are Gaussian, right? And so we'll see that. That'll be that's the easy step because it's just w times, a Lipschitz function of my initialization. And then, you say, okay, well, if life is good up until iteration t, right? If I've got all of these things are asymptotically Gaussian up to iteration t, then I want to show at iteration t plus 1, right? I still have this Gaussianity. And so, in short, the papers that prove this are 50 pages long or something, right? And kind of the reason for that is you have to the way that you do this is you kind of take every sort of, every element of the iteration, so the BT, the MT, W times MT, the HT, and you kind of show that like their norms concentrate on things predicted by the state evolution. So each step of the inductive proof, you know, you have to prove that like 6 or 7 things like concentrate at the same way, in the correct way, and you know, show that all your kind of complicated dependencies get canceled out and these sorts of things. So we aren't going to go through the proof like exactly, right? At some point, I'll just ask you to trust me, you know. But we can at least see like the first step and kind of get an idea, like a taste for what's done. So I'll mention like, okay, so with this, with the initialization, so you should probably be thinking about this as being just like a constant vector. In many problems, you just, like, you're gonna initialize with like the all 0 vector or all 1s vector or something. It turns out in like low rank matrix estimation specifically, which we'll talk a little bit more about, that's not going to work if like the, you know, the elements of your spike are mean 0, so you have to use kind of an informative initialization, in which case you would initialize with like a spectral estimator or something, and you know, then you don't have this independence. But that, you know, those are kind of technicalities we'll get to down the line. So for us, it's like we should be thinking about this as just like a constant vector independent of the matrix. Okay, so so let's think about like the first step in the induction, right? So what do I want to show? I want to show that the empirical distribution of H1 converges to normal 0 tau 1 squared. Okay, where, okay, H1 is just my GOE matrix times F0, H0, right? And tau 1 squared is this, right? Okay. So kind of the idea is the following. So, you know, kind of conditional on H0, right? So, okay, so we should probably think about this as being deterministic, but it could be random, right? But either way, you know, this is something we know, right? Because H0 is independent of my GOE matrix. It's not too hard to work out the distribution of this guy, right? So kind of the idea is, all right, I'm thinking of this as, you know, either being deterministic or in my conditioning sigma algebra, right? So this is a vector that's deterministic and fixed, right? This is a symmetric Gaussian matrix. And so you can convince yourself that this is going to be Gaussian with mean 0. And then the covariance matrix is given by the following. So it's so this guy times an identity matrix of size n plus a sort of rank 1 spike right? So sort of the idea is that, okay, if this were just like an IID Gaussian matrix, right, then we wouldn't have this term here, right? Then, you know. But since, you know, this is like a symmetric matrix, we kind of get this extra sort of rank 1 spike in the covariance. But okay, the sort of idea is like, okay, well, this term, right, this guy converges to tau 1 squared, right? This is my like assumption here, right? So, 1 over n norm f0 h0 squared converges to tau 1 squared. All right, so this is eventually going to be like tau 1 squared times the identity, right? And then the kind of the second point I claim, right, is, okay, so this is vector transpose, right? And these are kind of constant order things. So this is a matrix, with a bunch of constants, but it's hit by 1 over n, right? So, element-wise, all of these guys are going to 0, right? So 1 over n, f0 h naught, f0 h naught transpose goes to like a 0 matrix, basically. But then this is kind of the result, right? So this guy gets killed off, right? This is eventually tau 1 squared, right? And so, now we've convinced ourselves that, like, if we look at the elements of this vector, right, they're each going to normal 0 tau 1 squared, hence, like, the empirical distribution converges to the same thing, right? Okay. Erase this. Okay, so now let's think about the second step. All right, so my second step, okay, so now, so H2 equals W M1 minus what are my indices? B1 M0, right, where these are just like F1, H1, F0, M0, right? Okay, and we want to show, right, that this, want to show P hat H2 converges to normal 0 tau 2 squared, right? Okay, so the difficulty, right, like you can kind of see the difficulty like immediately, right? So, W isn't independent of M1, right? Because M1 is, F1, H1, right? And H1 is constructed with the W, right? So, immediately, like, this isn't going to be Gaussian, right? So WM1 isn't Gaussian. Okay, so kind of the idea is like, all right, like let's pretend, instead, we have a kind of independent GOE matrix in there, right? So pretend, we study H2 equals W tilde M1, where W tilde is GOE, independent of M1. Right, so it's like, okay, so if we just iterated this with like a completely independent GOE matrix, then, we could kind of now repeat the same argument, right, to get, then, p hat h2 converges to normal 0 tau 2 squared, y, where, tau 2 squared equals, lim and n of 1 over n m1 squared. Right, we would do the same argument. We'd be like, okay, the actual distribution of this is like, this guy times the identity plus the spike, but the spike asymptotically doesn't matter, and so we get this, right? But, this is then just lim n 1 over n f1 h1 squared, and, okay, so you can argue, this is going to be F1, H1, what am I thinking? Sorry, F1, tau 1z squared, z normal 0, 1, right, where you kind of, now you're sort of using the fact that this is, empirical distribution of this guy is asymptotically Gaussian, right? So eventually this is, this converges to its expectation, right? And, now this is tau 1 squared as we defined it here. Somehow I got off of my my indices. Let's see. I want tau 2 squared. There we go. Yeah. Right. Okay, so kind of the idea is like, okay, if we're just iterating, completely new random GOE matrices with sort of, these vectors with the Lipschitz functions, then we'd get this kind of recursion. Of course, this was pretend, right? So kind of the idea is that the role of this term is to make it such that, this is still true even when H2 is defined like this, right? So kind of the idea is that exactly asymptotically, this term is going to cancel out kind of the dependence between the W and the M1, right? So this term has a lot of names. So, you might call it a debiasing term. Right, so, okay, so I'm thinking of the debiasing term as being like, H2 equals W M1 plus B1 M0. So this guy is my debiasing term, where again, B1 is like the sum of the first derivatives. Right. So another name for this guy is the Onsager correction term. And so this kind of pays homage to the some of the ideas, at least for the proof, come from the statistical physicist. Right, so sort of, I'll cite the paper later, but Bolthausen kind of proved the first sort of, for a specific IMPA algorithm solves the spin glass equations, and so Bolthausen first proved kind of the state evolution for that specific AMP algorithm. And then Javimard and Montanari gave the first theoretical proofs for AMP, and they kind of borrowed from the ideas from Bolthausen. And so the kind of the roots of this term go back to kind of that literature for solving these sorts of, or thinking about these sorts of equations as, for use in spin glass and like a specific form of like the tap equations. But okay, so this is, an Onsager correction term, right? This is negative, sorry, this should be negative B1 M0, or a debiasing term, and it kind of ensures, at least asymptotically, that H2 has the correct distribution. Asymptotically has the same empirical distribution as, W tilde M1, where W tilde is like our independent matrix. Why it's like I don't have a good story for like why it actually takes this form. I mean, in some sense, this comes from like Stein's lemma, right? We've got a lot of Gaussians floating around, so kind of like how well, I'll talk a little bit about how you prove the inductive step, but it's sort of like, you assume that this has the distribution that you want, and you analyze the error from that distribution, and you need things to cancel out, and essentially kind of the crucial step is like an appeal to Stein's lemma to get the cancellation with the B1s here, sorry. But yeah, it's beyond that, there's not like a great story for what's happening here.
So that's where Gaussianity comes from, because in the first step,
Yeah, exactly. So this is like, the role is, now we have some complicated dependencies here, right? And the role of this guy is to kill those dependencies, so you keep going back to Gaussianity at each iteration. Yeah. So it's kind of, so I'll on probably next week at this time, I'll talk a little bit about how you can use AMP to minimize like random cost functions. So in particular, things like, the lasso cost function and these sorts of things. And it turns out that AMP acts like a kind of like a ADMM algorithm. And so, you can look, if you compare like the AMP algorithm to like the proximal gradient descent algorithm for the lasso, which just is like iterative self-thresholding, the difference is in this like Onsager term. Otherwise, like what AMP does is self-thresholding, but then you correct it, so you get the Gaussianity. And so there it's sort of like, this is like more of like a momentum kind of term, like a la Nesterov or something. So, I think that it has a number of kind of different interpretations depending on the problem at hand. But yeah, in some sense, the role is to just cancel out the dependencies that build up, so you get exactly Gaussian. So what I'll try to do is, okay, so in the last little bit, maybe what I'll try to do is look a little bit at the inductive step and how it's proved, and you can kind of see how things like build up to retain the Gaussianity. I think I like this because there's kind of like a really cute trick in the proof where basically like the way you prove it is you sort of study like the distribution of the GOE matrix conditional on all of the past iterations. And that's sort of the key concept that allows us to prove things. And this is what Javimard and Montanari credit Bolthausen for the idea. This is like called the Gaussian conditioning trick. And it's sort of, it's kind of clever, I think, and it gives us like the way to prove these things. Okay, so let's look at the inductive step. Okay, so if I look at the inductive step, okay, so, all right, so here, right, so I have h t plus 1 equals w mt minus bt mt minus 1. And I want to show that empirical distribution of ht plus 1 converges to a Gaussian mean 0 tau t plus 1 squared. Okay. Okay, so the first step is you know, the first step in these proofs is like Gaussian conditioning trick, right? Which basically says the following. So I'm going to think about having a sigma algebra that I'll call ST. That's the sigma algebra generated by, you know, kind of all my previous iterates. And you know, what I want to do is decompose this GOE matrix kind of conditional on, you know, this sigma algebra. So what I'm sort of asking is, okay, so what's the distribution of W, my GOE matrix, now that I know, you know, all the previous steps of the algorithm? And kind of, you know, the idea, right, is that if you think about, you know, this, well, it's like, okay, so now I have HT is like W times MT minus 1 and some other things. You know, HT minus 1 is W MT minus 2 and some other things. So sort of like the idea is, you know, you want to look at the distribution of W conditional on you have a bunch of like linear constraints given by the previous iterates of the algorithm. And it turns out that this is a distribution that we know. So essentially, this is, you know, this is now, you get like a projection. Well, so you know, okay, so this is equal to the expected value of the matrix given your sigma algebra plus a projection away from the span of the sigma algebra. Right, so, okay, so what I mean is, okay, so I'm thinking PT is like the orthogonal projection onto the span of these vectors. So, you know, this is I minus PT, right? So that's orthogonal span off of it, right? And kind of the idea, right, is that these are orthogonal matrices, right? And I have the rotational invariance for the GOE. So in particular, you know, I can write a tilde here, right? And this remains true, right? Because like the property of GOE matrices that I said we would use, right, is that if you hit it with orthogonal matrices, it's still GOE, right? So this is an equality in distribution, right? So now kind of the idea is I have, you know, a piece.
So you say basically, okay, there's a part that's just in this expectation, and the other thing, except for these projections, independent.
Yeah.
What have you seen up to now?
Yeah. So now we have a piece kind of in the direction of my sigma algebra in some sense, and a piece orthogonal to it.
It's very high, and you're projecting onto a very high-dimensional subspace. So that's basically done to the.
Yeah. Yeah. Right. So. Okay. So then, you know, you can kind of use that here, right? So now if I'm thinking about, okay, so let's think about the distribution of HT plus 1 conditional on, you know, the sigma algebra of my previous iterates, right? And so what I'm going to do is just, you know, plug in this decomposition. And so, you know, I get that this is like, okay, so this is now expected value of W given the sigma algebra times MT minus BT MT minus 1, and then I have this independent piece, right, which hits the MT plus PT perp W tilde PT perp MT. Kind of, and the idea here, right, is so this is all now, conditioning on the sigma algebra, this is all deterministic with respect to the sigma algebra. And this guy is random, right, but it's independent of everything else, we've seen so far. So this is random, but independent of. So sort of like, the final step, which, I'm not expecting you to be able to see how we get there, but, there's 2 pages of proofs later. What you can show, right, is that this is equal to, a sum of your previous iterates, so 0 to t alpha I hi, right? So this is like deterministic, right? And basically depends on the state evolution. These are our previous things. You get kind of a tau t perp, let's say, z, where this guy is, independent of your previous iterates, and some deviation term, right? And so kind of what you can show is that, okay, so this guy you can argue goes to 0, right? In the sense that like 1 over n, 2 norm of this converges to 0, right? So your error goes to 0. Now it's like, you have a linear combination of the previous iterates, but you kind of like unwrap this conditioning, right? And these guys are all Gaussian by the inductive step, right? So now you have, your current thing is, a sum of things that are Gaussian by induction plus a new independent Gaussian piece, and you can kind of then, okay, all of these are mean 0, right? And you can convince yourself that the way that they sum gives you back like the state evolution sort of predictions. So that's really, there's a lot of steps missing, but basically the point that allows us to do this is kind of this sort of the fact that, if we look at a Gaussian matrix and we condition on a bunch of linear constraints, we know the distribution of that exactly, which then allows us to kind of analyze the distribution of these iterates too. Okay, so maybe just to wrap up, what I'll do is I'll state the main, I'll state like the kind of informal thing I wrote here more formally. And then, next time what we can do is start from our abstract AMP iteration and see how we get the AMP for like low rank matrix estimation. Okay. So, so the first thing is I want to define a class of functions that are called pseudo-Lipschitz. So kind of the idea is in the beginning, many of the theoretical results for AMP were stated in terms of pseudo-Lipschitz loss functions. So essentially a function psi from, Rm to R is, we'll say it's in the class of pseudo-Lipschitz functions of order k with constant c if if what? Okay, so if psi x minus psi y is upper bounded by c times 1 plus x k minus 1 plus y k minus 1 times x minus y to the, I think that's right. Okay. Right, so, okay, so this is just a kind of a relaxation of like the Lipschitz property, right? So if I ignored this, this would be Lipschitz, but now I back off the Lipschitz a little bit. So like what this is saying is roughly, you know, if we're pseudo-Lipschitz of order 2, then roughly psi is like a quadratic. So roughly, what do we have? You know, psi of x is like a constant times x to the k, right? You know, so pseudo-Lipschitz of order 2, right, says like functions with at most quadratic growth, right? So if we're looking at like, you know, in particular, this allows for like psi of x equals x squared, or, you know, psi of x y equals x times y, or x minus y squared, for example. Right? So I define this because, you know, kind of the early results in like the AMP theory were, you know, stated in terms of pseudo-Lipschitz loss functions, right? So, okay, so some assumptions for the theory. Okay, so, you know, W, GOE, independent of my initialization, right? Okay, so the empirical distribution of F0, H0 converges to some distribution, let's call it, I don't know, capital F with, you know, bounded kth moment, right? So nothing can happen that's too wacky with my initialization. And then, you know, some regularity on these denoising functions, ft, right? We assumed a Lipschitz, but you need a little bit more than that. Some statements on their weak derivatives and these sorts of things. So I'll mention, right, so, okay, so these are, like, sometimes I'll call these, like, denoising functions, right? And the reason for that is because when we think about AMP actually for a specific problem, the term that we have in the input, so here it's like, it's H, right? We show that that's Gaussian. So when we're thinking about signal estimation, usually the input will be asymptotically like the signal we want to estimate plus Gaussian noise, right? And so then you want to design these functions so that they denoise in that way if you have, you know, thing plus Gaussian noise. Right? Okay, so then the main theoretical results are the following. Okay, so here, okay, so this is, sorry, I was saying Javanmard and Montanari, but it's Moshe and Beati and Montanari that actually did the first theory. Javanmard did some later, they're both students of Montanari who did some of the early AMP theory. So this is 2011, and this is also, you know, Bolthouse proved this again in a special case, you know, to solve the tap equations. Right? So basically the result says, okay, the following. So for any psi from R to R in pseudo-Lipschitz of order k, and any t greater than or equal to 1, what do we have, right? So limit an n of 1 over n sum I equals 1 to n of psi h t I converges to almost surely to the expected value of psi tau t z, where, you know, this guy is normal, 0, 1, right? So this says we can, you know, we can take the elements of these iterates and put them in a pseudo-Lipschitz function, and then, you know, this is going to converge to some deterministic thing, right, where the deterministic thing depends on the state evolution, right? So not uniform. Okay, so you can give a joint distribution statement. So I can say something like limit n 1 over n sum psi hi1 ht you know, this guy. Sorry, so this should be an equality, right? So almost sure equality, right? You know, like an expectation of psi, you know, tau 1 z1 tau t zt, where now, you know, like, you know, these guys are kind of the state evolution we saw before, but now we have like some dependencies between the z's, but you can also characterize like the covariance matrix of the z's with a recursion. Yeah, so you can get a joint distribution statement, and it is going to be uniform over pseudo-Lipschitz loss functions. So you can strengthen this to say, so, you know, okay, so this is sort of a remark. Okay, can strengthen to uniform over pseudo-Lipschitz functions, right? So in particular, I could say something like soup over psi and PL KC, or let's say like K1 to be concrete, right, of, you know, 1 over n sum psi HTI minus all right, so that's going to go to 0, right? So I can be uniform over the pseudo-Lipschitz functions. And, you know, this is going to, then you can argue that this implies convergence in Wasserstein as well, right? So, you know, like if this is 2, you can argue that P hat HT converges in, you know, Wasserstein 2 to normal 0 tau t squared. Yeah, so okay, so initially the language was in pseudo-Lipschitz functions. Now I think a lot of the language around the theoretical results are in convergence and Wasserstein. But, you can, once you get here, it's pretty straightforward to get there as well. Okay, so I think maybe I'll stop a few minutes early today, and then, we'll make the connections to low-rank matrix estimation next time. I'm happy to answer any questions. I know it was a little bit dense today, but it's the name of the game, So. All right, thanks.